All right, so we have the recording going. I just have the home screen opened up here in my student mode so we can look at our screen. And I do want to note a couple of things, like if you're wondering, hey, what do I have to do? There's this handy dandy little to-do bar on the right-hand side of your screen that shows you things that you haven't done. So as you get those done, those things will automatically go away. So that's one way to keep on track with what we're doing in the class. And we are getting towards, we're getting towards the end of the lectures and stuff. And of course, there's a lot of stuff that I could present and share, but this is only a 1-unit class, so I'm trying not to kill you guys. But with that, there's going to be some snap-on information you can do. And so there's lots of resources you have in this course. There's probably about 3 units worth of information for you, honestly. But again, I'm trying to make it palatable for you. Another way to check and see where you're at with coursework would be to go over to the calendar tab on the other side. I'll clear out my drawings and you can see what's coming up next. So here we are, we're on November 3rd. Of course, it shows our class that we're doing right now. And I kind of push stuff back a little bit, so our next assignment isn't due for a little bit. And so we have plenty of time before we jump into our next quiz and establishing a condition. I wanted to make sure that, because I'm going to talk about the things that relate to these assignments tonight, right now. And I want to make sure that for folks that aren't able to tune in with us live, they have enough time to watch the video. It usually takes me a few days to get it posted to the internet there, and then they can watch it and they should be able to complete these activities. So using the course calendar, another way to stay up to date on what's going on in our class. All right, I'll clear out those drawings and I'm going to change my screen share so that we can jump into tonight's presentation on fuel trim. And what we'll do is we'll make that share full screen and we'll get going. All right, so using fuel trim to direct diagnosis. Now, I do want to say that, remember our last class session, one of the things we talked about, whether you're using our little scanner interface and our car scanner app, or you're using a professional scan tool, is trying to get the maximum amount of information out of that tool. And a great method to do that is by graphing out the data. So you'll notice that this scan tool here, we've selected data graph mode. And so we're looking at short-term fuel trim, long-term fuel trim, and our engine RPM. And we can definitely see some trends here going on. And hopefully by the end of the night, this screen here with these data graphs will make sense to you. Okay, so with that, let's jump in here. So as we're jumping in, a little bit of review. We've talked about this multiple times, about the front door versus back door, right? All of our sensors coming in, even things like the oxygen sensor that we talked about last class. This is front door information. The computer takes that, processes it, sends it over to our scan tool. So that means that our scanner, of course, is backdoor information. It's processed. And there are times where the scanner could possibly lie to us or mislead us, especially if we're in the manufacturer mode or side of the manufacturer side of the tool. But still, that scanner is very, very powerful. And so we just have to keep that in mind. So I'm always a little suspect, and really it's always better to measure sensors directly. And that's why we like to say, we like to compare our scan tool to, if I can switch to my next slide, we like to compare it to a compass, if you will. It kind of gets you going the right direction, but usually you're going to need your multimeter, your oscilloscope, some other tool to actually pinpoint exactly what the problem is. Okay, in our class, we've also introduced you to a basic 8-step diagnostic process. We're going to use this one again tonight to do some diagnostics on one of your guys's cars or on a fellow student's car. So hopefully that'll be kind of fun and interesting. And again, you're going to take this and kind of make it your own, and you might modify some stuff. But if you follow this process, you know, it should get you going towards the right direction of making a successful repair. All right. So with all that, let's go back to this. We're looking at the codes. And remember with OBD2, when it came out 20 plus years ago, this was a huge leap forward, because before we had all kinds of different codes. Now we have a standard alphanumeric coding system, which means that for instance, a P0171 means the same thing on a Toyota as it does a Ford or a Chevy or even a Volkswagen. If this second digit is a 0, it's a generic code, and that means it will be the same on any make model that is OBD2 compliant, which is awesome. Now, you'll notice that the vast majority of codes we've been focusing on that we can really get good information on with generic data are usually powertrain codes, because the goal with OBD2, of course, is to monitor those emissions over the life of the vehicle. And so it's the most robust in the powertrain area, right? So we can get computer codes, network codes, and stuff like that. But mostly what we're going to be accessing is powertrain related. But there's still a ton of diagnostics, and it's the really important stuff of why does my car not run correctly type of stuff, right? So remember that if you have a generic code, the second digit is a 0, you could look, it doesn't have to be specific. You could look up any OBD2 code chart and find the definition of that code. So we will clear those scribbles and keep pushing forward. Oh, don't forget about the transmission codes there. All right. So notice that our code on the last screen, we had a P0171. Well, that is a pretty common code. In fact, that's a fuel trim code, which is our hot topic of the night. And with fuel trim, you know, we tend to see quite a few of these P0171s, P0172s, bank 1 and bank 1 2 lean. Here we have that. And I want to say this little shot is off of the scanner app that's built into CDX. So those are pending codes. Remember that a pending code, it's ran the monitor, it's set the pending code because it's seen the failure. If it's a type B code, it would not turn on the check engine light yet. It would have to run that monitor again, see that failure happen a second time consecutively, and then it would turn on the check engine light. And that's why my tip was always verify your repairs and check for pending codes after your test drive, right? So we have a couple pending codes on this thing for the vehicle running to lean, a 170, 171 code here. And with that, I want to point out that, hey, the command is always opposite the condition. In fact, last week we were talking about oxygen sensors, or I should say a couple weeks ago, but our last class, we talked about oxygen sensors, and we talked about how they go, you know, rich, lean, lean is low here. So whenever the O2 sensor says, hey, you're rich, I'm going to put an R right there, the computer's command is going to be, okay, well, lean out the air fuel mixture, go lean. And then when the O2 sensor does that and says, hey, now you're lean, then the computer's going to say, okay, now go rich again. And it's that cycling back and forth, that rich lean cycling that gets us on average at that stoichiometric air fuel ratio. So the command is opposite the condition. So if we are saying, hey, the system is too lean, what we can then learn from that is that, hey, the computer sees the O2 sensor always staying down here. It's always saying, hey, you're lean. It's low too often. And the computer knows, hey, that's not right. And it's trying to correct the condition. It's trying to richen it up, but it can't get there. And so that's what that code is telling you, is that the computer has identified that the O2 sensor signal is too low for too long of a period of time. And it's trying to correct it, and it can't get it there. Well, what is fuel trim? Fuel trim is that amount of correction. And this isn't something new. Well, obviously OBD2 has been around for a long time, but even before OBD2, General Motors had a fuel trim function on their computers, on their fuel injected vehicles, and they called it integrator and block learn. So I know I had a few of you in the shop playing around with some old GM cars. Yeah, integrator and block learn were the GM version, the GM OBD1 version of fuel trim. So let's dive into that. What exactly is it? Let's peel back the layers on that for a bit. So to do that, we have to understand open loop and closed loop. Now, oops, let me go back. Open loop, I'm looking at all the computer's sensors, but I'm not really listening to the O2 sensor yet. So here I have a freeze frame here from my scanner, and it says, hey, fuel system status, hey, we're in open loop. Why? Due to insufficient temperature. So we're in open loop right now. Well, what is open loop? I'm going to be looking at the coolant temperature. I'm going to be looking at engine RPM. I'm going to be looking at mass airflow or manifold absolute pressure and come up with a load value. I'm going to be running off my base programming, but I'm not looking at the O2 sensor yet and responding. Actually, I shouldn't say I'm not looking at it. The computer's looking at it, but it's not really listening to it. Well, what happens when we go into closed loop? When we go into closed loop, then the computer begins to listen to what the O2 sensor is telling it, and it will modify the amount of fuel it gives the engine accordingly. Okay, but in closed loop, or I'm sorry, but that's in closed loop where it listens to the O2 sensor. In open loop, it's not listening to that O2 sensor, and it's just going off of what's programmed in its memory banks, if you will. Okay, so let's clear out those drawings, and we'll keep moving forward. So what I have here are some fuel calculations, or essentially the fuel map. Okay, so what air fuel ratio do I want at whatever speed and whatever load? So these maps are really more three-dimensional, but to make us understand them a little easier, we typically draw them out and break them up into 2 dimensions that we can put on our computer screen, or I can draw on the whiteboard, or I can draw on our Zoom screen here. And so what you can see here is we have our engine RPM going across the screen, right? Higher and higher RPM. And then we have our load from low to high. And of course, we've taken speed and load, and we've tabled that out for different air fuel ratios at different speeds and different load values. So you can see from this one, we could run pretty lean air fuel ratios here when we're at low levels of load. And usually where we're driving around this kind of main section here, we're going to be running our stoichiometric or air fuel ratio, because that's our normal like cruising speed, driving around through traffic, that type of stuff. When we get the pedal to the metal and we're wide open throttle, extremely high load, you can see now is where we give the engine more fuel, and we do that to keep it safe. Now, if this stuff kind of interests you, you know, that's good. It kind of interests me as well. We actually have a class where we do some of this programming, where we go in here and we change or modify these maps. Now, this table is normally just programmed into the computer, the PCM, Powertrain Control Module, and we can't do anything about it. We can't change it. The engineers at whatever manufacturer, Chevrolet, Ford, Mazda, they program that stuff in there. We can't change it. However, if we have some type of aftermarket fuel injection system, some aftermarket computer, let's say we have a Haltech or a Motec or a Mega Squirt or a Motorsport Electronics ECU in there, well, then we would have the ability to go in and start to modify these different values in these tables. And that's really really fun, really interesting. And you can unlock quite a bit of power. Now you can see from this chart that I put up here, I've divided up the chart into areas where, we're usually not over here, right, at extremely low loads, and we're, mostly we're going to be cruising. We're going to be at idle. We might be here cruising down the road. We have another rarely used section. We might floor it and do an acceleration, a wide open throttle. So you can break this map into the areas that you use more often that have to be more dialed in. And, this map of fuel, it's a compromise. It's a compromise between getting the vehicle from the manufacturers. It's a compromise between fuel economy, performance, and you guessed it, vehicle emissions. So if I didn't care about, fuel economy or emissions, I could modify how much fuel the engine gets and maybe unlock some more power out of that engine. If I was going for something that was, just really high economy, getting the maximum miles to the gallon, again, I could change this map so that my amount of fuel that I give the engine is different to squeeze out more miles per the gallon, right? So any factory computer, this fuel map is going to be a compromise on fuel economy, performance, emissions. And the other thing I should kind of add in there is I got to keep the engine safe. I don't really want to be burning up pistons in this engine. So when in doubt, they'll usually give the engine more fuel at high loads. And so if I change my screen share a little bit and I clear out some of these drawings and I make the gray box go away, you can see that the air fuel ratio here on this chart goes pretty darn rich here when we get up to high loads on the engine, even at high speeds. And they're doing that to keep the engine safe, keep it out of detonation, keep it from burning itself up. Okay, so now you know a little bit about the fuel map, how much fuel is going to be programmed into that computer to be delivered to the engine. Think of that as this fuel map controls the amount of time the fuel injectors are on or open, spraying fuel to your engine. Okay, so we'll simplify it out a little bit, and you can see again, I have my load. So the higher up my load, the higher up I go, so up the chart that way. So more air going into the engine, it's under more load, that goes up that way. Of course, my RPM is going this way. And if I related this to a physical time value, I could say, okay, well, this is milliseconds of what? Well, this is going to be milliseconds of injector on time. How long do I turn on those fuel injectors? So here I'm at, basically idle speeds, low loads, and maybe I'm, 3, 4, 5 milliseconds. I'm cruising down the road. Maybe I'm, 12, 13, 14 milliseconds. I start getting to higher and higher loads. And now maybe I'm 20, 30, 40 milliseconds of injector on time. And so even if you're getting into a little programming, we usually program in volumetric efficiency numbers, which I'll get to that in a minute. Really what the computer is going to do is from whatever you type in those boxes, it's going to calculate a certain amount of on time for how long it turns on the fuel injector. So maybe at 4,000 RPM, at whatever load this is right here, it determines that 24 milliseconds is the right amount of on time. Okay, so that's what's programmed in the fuel map. And when you're in open loop, so I'll write that down. When I'm in open loop, I'm just going to do, if I'm the computer, I'm just going to do whatever it says to do in this chart. So if the chart has 24 milliseconds on there at this speed and this load, that's what I'm going to do with the fuel injectors. I'm going to open them up for 24 milliseconds. If I'm at this speed and this load, I'm going to be at 11 milliseconds, right? So I'm just running based on the other sensors and stuff on the engine, what my engine speed is and load, and there is modifiers to this table based on what the coolant temperature is and other things, but I'm just running off of that. Well, a big modifier to this table would be when I go into closed loop is I come up with this value of, let's say, let's pick this one right here. Let's say 11 milliseconds. And the O2 sensor then is going to see that and it's going to say, hey, man, you're rich or you're lean. If I'm in closed loop, I'm going to listen to that O2 sensor and I'm going to modify this number based on that. So if I did 11 milliseconds and the O2 sensor said lean, well, what I would do, if I'm the computer, the command is opposite the condition. So if he said I'm lean, the command is going to be to go rich, which means that maybe I'm going to open this up to 12 milliseconds. And then I'm going to see what's the O2 sensor say now. If he still says I'm lean, I'm going to open it up to 13 or 14 milliseconds. If he says I'm rich, maybe I back this off to 10 or 9 milliseconds. So closed loop, basically you're going to start modifying this table based on what the O2 sensor is telling you. So that's great, but where are we going with this? Well, let me clear out these drawings and move us forward. Okay. Remember that the O2 sensor basically is like an O2 comparator. He's comparing the amount of oxygen outside the exhaust with what's inside the exhaust. And when there's a difference, that's how he makes a voltage, right? And most of these sensors produce a maximum voltage of just over a volt. Well, that's fine and great, but a lot of cars have moved away from oxygen sensors. They've moved to air fuel ratio sensors. And guess what? Those air fuel ratio sensors, man, they look a lot like an oxygen sensor on the outside. However, where O2 sensors needed to get up to 600 degrees to become hot and active, air fuel ratio sensors usually run double that. They run 1200 degrees Fahrenheit before they start working. And that means they take quite a bit of current from the computer. They actually have a heater element in there that can pull up to 8 amps. But think of this as a O2 sensor that can operate over a wider range. And a lot of things that we talked about a few weeks ago about oxygen sensors still hold true with air fuel ratio sensors. Like eventually these sensors are going to fail. And essentially it's like having 2 O2 sensors in one single unit. And so that would make sense why we're running twice the temperature. And of course, I'm really oversimplifying it, but basically it sets up multiple chambers within the sensor, and it allows the sensor to monitor the air fuel ratio over a wider range. So where a regular O2 sensor would say rich and lean, the rich, that could be, anything richer than 14.7. So if I'm at 14 to 1 air fuel ratio, can't get the dots to go. If I'm at a 14 to 1, that's still going to be rich. And if I'm at 15 to 1, that's going to be lean. Well, it wouldn't necessarily know the difference between 15 to 1, and let's say 17 to 1. So the downside of a regular oxygen sensor is he's going to know, hey, I'm richer than stoichiometric and I'm leaner than stoichiometric, but he doesn't know how rich or how lean. The air fuel ratio sensor can tell the computer how rich or how lean. Okay. The signal that it generates is a little different. Some of these sensors, if you look at the scan data, they'll show you a voltage reading. Other sensors will show you current. Mostly the computers monitor the current flow. And I'm not going to get into all the nitty gritty details of how this sensor works, just that it's kind of like two O2 sensors in one, and it gives you a wider temperature range or a wider air fuel ratio measurement range. And that means it runs at a higher temperature range. And these things tend to stick in there because they run so darn hot. I've had several cars, you go to replace an air fuel ratio sensor and the threads in the exhaust manifold get stripped out because these suckers just run so darn hot. Okay. But they do have a failure. They do have a lifespan to them, like an oxygen sensor. And so it's not outside the box at 80, 90, maybe 100,000 to have one of these guys fail on you. Okay. So now we know we can have an oxygen sensor, or we could have an air fuel ratio sensor. And the signals they produce are going to be a little different, but they're still going to tell the computer, am I rich or am I lean? It's just that the air fuel ratio sensor, he can tell that computer how rich he is or how lean he is running that engine. And so here would be a wiring schematic. This would be like your typical 5 or 6 wire sensor here, like you might see on a Honda, something like that. All right, so let's bring this back to the fuel map and talk about how either the oxygen sensor or the air fuel ratio sensor again is going to is going to affect this thing. I have on the screen here, remember that the fuel map's programmed into the PCM, and I say it really uses VE. Well, VE stands for volumetric efficiency. And so here I'm looking at a screen from a Haltech, and this is just like what we use in our AT325, our engine performance testing and tuning course, where students who are interested in this stuff can actually go in there and do some tuning and dyno runs. And so these numbers here, if I just, I don't know, highlight one here, we're saying, hey, we're telling that the computer that the engine's efficiency at that particular RPM level and that particular load is 79.2%. That percentage of volumetric efficiency would then relate in the computer to a certain amount of on time. So what is volumetric efficiency? Well, volumetric efficiency really is comparing how much air has entered the engine for real versus theoretically how much air should be coming in there. The swept volume or the displacement, right? You guys have probably heard that saying, there's no replacement for displacement. The displacement of the engine is its internal size. If you think of your engine like a pump, like how much air would it pump out? So maybe I have a 5.7 liter V8 engine, right? That's a 350 cubic inch engine. So that would be its displacement. Well, the volumetric efficiency is comparing that. So here I have an engine that's 100 cubic inches, but when we measured it, only 80 cubic inches of air entered the engine. So we would say its volumetric efficiency would be 80%. Now, for old engines back in the day, 80% was pretty good. Most vehicles today are going to be in the mid 80s up to the low 90s. Cars that are turbocharged or supercharged where we're pushing the air fuel mixture into the engine with some form of a compressor can get over 100% volumetric efficiency. But again, what is it? We're comparing how much air is actually entering the engine versus its displacement. Okay, so if I'm running at 100% volumetric efficiency, I'm completely filling the engine with air fuel mixture on its intake stroke. And that's pretty hard to do. So of course that's at wide open throttle and all that type of stuff. If I start closing the throttle, then the volumetric efficiency is going to go way down because now I'm restricting how much air can enter the engine. All right. So now let me go back a couple slides. Now that we know what volumetric efficiency is, and it's a huge thing when it comes to performance, because if we think of almost all of our performance modifications, whether it's putting a different intake on there or a high flow exhaust, it's all about making the engine a more efficient pump, which should help improve its volumetric efficiency. So what you can see here is at lower throttle levels and loads, I have lower volumetric efficiency numbers. And where my volumetric efficiency numbers are the best is where I have, you know, moderate speeds and high load values there. All right. So fuel map modified. Now we're going to do the fuel map modified. Remember that we looked at this fuel map before and we talked about, hey, based on the O2 sensor, and now I could say also the air fuel ratio sensor, if the computer said, hey, I want the fuel injectors to be open for 11 milliseconds, based on what that sensor is, it could then fine tune this number. So if the O2 or air fuel ratio sensor said, hey, you're lean, the computer's command would be to, hey, go rich. And so maybe he's going to go from 11 milliseconds to 12 or 13 milliseconds. And then he's going to look at that O2 or that air fuel ratio sensor, and he's going to see, okay, am I rich now? Or if it's an air fuel, how rich am I, right? And he's going to adjust what's programmed in this table, or he's going to modify it based on what that O2 sensor or air fuel ratio sensor says. Now, something that I didn't make a big deal of tonight, because I'm pretty sure we talked about last time, is remember to go into closed loop. We usually need a few things. We need the engine to be warmed up. We need enough time to have elapsed, right? So some computers will have a little timer circuit in there. So adequate amount of time. And we're going to need an active O2, or I'm going to say air fuel ratio sensor. So O2 and AFS, and I also say no other codes. No other codes that would possibly impede its ability to go in the closed loop. There's always, you know, the possibility that it could be setting a misfire code or something that might prevent it from going into a closed loop. Like for instance, if based on the throttle position sensor or TPS, it thinks it's at wide open throttle, then if it thinks it's at wide open throttle, it's going to keep it in open loop. So
You go with your no. That was literally the whole year.
Hang on, let me mute Damien there, so we don't get so much feedback. So anyways, with that, hopefully this makes sense, is that when we go into closed loop, and remember the engine's got to be warmed up, we have to kind of meet all of these conditions, if you will, right? Think of that as your enable criteria. Then we're going to modify what's on the fuel map based on what the O2 sensor is saying or what the air fuel ratio sensor is saying. Well, what all of this background information has been trying to get to, the question is, what is fuel trim? Well, fuel trim is the amount of correction, meaning that if I had to modify what was programmed in that base map, if I went from 11 milliseconds to 3 milliseconds, well, how much did I have to modify it? Maybe I had to go to 15 or 16 milliseconds. That's a bigger correction. So it's really powerful to know, well, how much is the computer having to correct from its base programming? If we assume that the engineers did their job correctly and they programmed up a good fuel map, we shouldn't see huge corrections. And what they've given us is what we call short-term, or STFT, short-term fuel trim. And they've also given us long-term, or LTFT. So short-term and long-term fuel trim. And ideally, if the computer's not making any corrections here, this thing's going to be at 0%, meaning that it's exactly running exactly like the amount of on time that the engineers programmed into that fuel map. But realistically, every engine's a little different. Some fuel injectors flow a little better than others. We're going to fill up with different takes of fuel, and the fuel changes, throughout the seasons and different regions. And so there's all these variables in there. And so while ideally it should be 0%, what we really see is that plus or minus 10% is considered to be okay. So if my fuel trim is positive or negative 10%, and that's for the long term or the short term, that's going to be okay, and that's not going to set me codes. When I get too far out of that 10% zone, so maybe I'm at 20% fuel trim, or I'm at negative 32%, now's where I'm going to get codes. And you guys, as you probably guessed, if the numbers are positive, the computer's adding more fuel, it's adding more on time from its base programming. And if the numbers are negative, like let's say I programmed it as 8 milliseconds, but I'm only giving the engine 6 milliseconds on time, then that's going to be negative numbers. It's taking the fuel away. Okay, so positive fuel trim numbers, the computer's having to add more fuel versus the base programming. Negative fuel trim numbers, it's taking it away. Okay, so why is this, knowing all this, why is it so powerful? Well, first of all, it's one of the things that we can access with the generic scan tool. Now, I've wanted to have you one slide where we showed you like a MOTEC programming table here. You can see it's really a three-dimensional table. MOTEC is premier engine tuning hardware and software, and this is what you would really use in the motorsports world. Pretty awesome stuff. And again, you can see that it's an engine efficiency percentage. It's a volumetric efficiency. That's the number that you're changing, but ultimately it's going to shake out to a different amount of on time for the fuel injectors. You also have tables like this that you would adjust in this software for not only your fuel, but if you look at some of these different things, and again, we do this in the 325 class, we got our fuel, but look, there's tables for ignition, there's tables for boost and RPM limits and NOx sense. So there's multiple tables that as the EFI tuner, you get to adjust to make that engine run exactly how you want it to run, which is really, really fun and interesting. And that's why on a lot of vehicles, you can unlock a lot of power with the right tune, if you will. So, all right, but moving forward. Okay, so we talked about volumetric efficiency, that difference between how much air is actually going in the engine versus its displacement. And here's another way to, here's the formula to calculate that displacement there. And And we do this in the automotive math class. I usually will talk about it a little bit in engine class. And, it's a big one, right? If you think of your engine as a pump, we need to know the size of that thing. And you actually program this into the software on a lot of these aftermarket EFI systems. So fuel trim is that amount of correction. And just like I had manually wrote into the notes earlier, plus or minus 10%, hey, that's considered to be normal, okay, for short-term and long-term fuel trim. Now, GMs, they had their own on the OBD ones. They called it integrator and block learn, and essentially 128 was like 0%, where it was supposed to be was 128. And if it was numbers above it, it was adding fuel. And if it was numbers below it, was taking fuel away. And I like to be, again, plus or minus 10. So I like to be between, 118 and 138 is where I was looking to be. So are we having to add fuel or take it away? And if by how much? Now, remember a few classes ago, I said, when you're doing diagnostics, one of the things you're trying to do is establish a condition. Am I rich or am I running lean? Right? Maybe I have a misfire. And, the rich or lean thing is a big deal because, hey, if I'm running too rich or too lean, that could lead to a misfire. So I'm always trying to establish that condition. Am I running rich or am I running lean? Well, fuel trim can help me figure that out. So here I can see fuel trim for short term on bank one is pretty close to 0, right? He's bouncing around a little bit. He's at 0. He goes up, he goes down a little bit, he goes up. And he's doing that as the engine speed changes. And of course, as the engine speed changes, what does that mean? That means I'm going to different cells in that chart or that graph that we were looking at, right? We can see the long term went from 0, he went up to 6.25 negative. So he was taking that much fuel away. Then he goes, he goes up to -5, then he goes down to -6. So on average, he's taking fuel away. But again, it's not more than 10%. So I'm not really concerned too much about that. Now, how do these two guys work together? Well, I like to look at short-term fuel trim. I'm going to put a K there for that's the kid. That's the crazy kid who's running around the grocery store trying to get toys or candy or something like that. Long-term fuel trim, that's the parent. So the parent kind of lags behind the kid, not moving as fast, tired from working all day, and they're not going to be as active. But if the kid gets too far out of line, then the parent's going to step in and make a correction, right? Well, that's how these two factors behave. The short term, it's normal for the short-term fuel trim to move around all over the place. If he stays anywhere for too long, then that's going to cause the long-term fuel trim to make an adjustment and shift. So it's not uncommon to see short-term fuel trim. Maybe he goes up positive, and he gets up to maybe 11, 12%. And then what will happen is the long-term will move up. And then when the long-term moves up, the short-term moves down. So, those two things work together. The long-term, of course, is more of a long-term trend of how the engine has been running for a longer period of time, where short-term's bouncing around. Now, this is one of the things that can get cleared out of there if the vehicle's battery is disconnected too long. Sometimes on some vehicles, even with the code clear, or some vehicles have a fuel trim reset function there as well. And so you might disconnect the battery or do that fuel trim reset, and now the car's running a little differently as the computer has to relearn the amount of correction or the amount of fuel trim correction for each cell in that graph. So it lets me know if I'm rich or if I'm lean, because if I'm having to add, let's say, both long-term and short-term fuel trim, let's say both of those things were positive, I don't know, 15%. It's not crazy, but it definitely tells me that the computer's having to add quite a bit of fuel, right? So that means if the computer's having to add fuel, the command's always opposite the condition. So the engine is actually running lean if the computer's constantly having to add fuel. Now, if the computer's, if it's, let's say, negative 22% on fuel trim, what's taking fuel away? So that means that the car is running too rich. And so it's a great way for me to see, are we running rich or are we running lean? There is some caveats to this, though. Now, I should take a side note here and say, hey, the best way to look at your fuel trim, especially when you're driving down the road, would be to do a recording or a snapshot of the data. So on our little app, we could go to this data recording function, and that way we could drive the car, we could keep our eyes on the road and record what that fuel trim is doing, and you could see what the trends are as you're driving around. I would like to look at the short-term and long-term fuel trim and what the engine speed is, and maybe what its throttle position is to figure out those trends. Okay, that's going to be the safest way to do that, would be to leverage that data recording feature of your scan tool. And this is the next screen that comes up. Remember to enable it, you got to exit out. So fuel trim is very powerful, but there's a couple caveats I said, and here they are right here. The first one is, can I believe the O2 sensor or the air fuel ratio sensor? In that fuel trim is relying on this sensor giving the engine accurate information. So if this sensor is junk, or if it's giving it false information, then it throws the whole thing out of whack, okay? So if I have a dead oxygen sensor where it's always saying lean because it can't produce good voltage, then the computer could misinterpret that as, hey, the engine's running lean. And then you're going to see positive fuel trim numbers, and maybe it's actually making the engine run way too rich. Now, this was much more common on our OBD1 vehicles because they didn't have as good a diagnostics built in for monitoring the oxygen sensors. They didn't have a rise time test. They didn't do warm up cycle, So, they would just blindly listen to what this thing said. I had a Jeep once, it had 11% CO. I mean, it was running so rich, it was like black smoke out the tailpipe rich, and it was nothing more than a defective oxygen sensor, okay? So first of all, you have to ask yourself, do I believe the oxygen sensor? If I do believe the oxygen sensor or air fuel ratio sensor, then I can go from there and say, hey, it really is running rich or it's running lean based on that fuel trim. Well, how can I know that this is not lying to me? Because there's several things. I could have a defective sensor. I could have an exhaust leak leaking air in front of the sensor. So the sensor doesn't get a true representation of, the amount of oxygen in the exhaust. So maybe it thinks it's lean when it's really not lean. There's an exhaust leak there. So that could throw this sensor off. I could have other problems with the engine. I could actually have a misfire due to, let's say, a bad spark plug wire or a bad coil pack. And so instead of burning the air fuel mixture in that particular cylinder, it just pumps that air down in the exhaust. The O2 sensor sees that and thinks it's lean. And now it makes all the other cylinders that aren't misfiring and makes those suckers run too rich. So again, this isn't foolproof. We have to definitely, use our smarts to determine, is this lying to me or not? So I'm always looking for things like exhaust leaks and misfires. And then what I'll do is I'll do what we're showing in the picture here. Maybe I'll artificially enrich in the mixture with a little bit of carburetor cleaner, or I'll just goose the throttle. I'll open the throttle quickly. That should make the mixture go rich. I might make some vacuum leaks, pull some vacuum hoses, make the engine go lean, and I'll see if the O2 sensor or air fuel ratio sensor responds. And if it does, and if it responds how I expect, like I pull a vacuum line and the voltage drops on that O2, then I could say, oh yeah, it does seem like it's working. I believe it. Okay, so you have to be able to believe this sensor. And so there's, pretty quick checks. Obviously checking things like, if I had a lean fuel trim code, I would check fuel pressure. I'm always doing a visual inspection for vacuum leaks and making sure that my other sensors, their data looks correct. But once I believe the sensor, then I can go off of what that fuel trim is telling me in establishing that condition. Well, let's go back to another term we talked about tonight, volumetric efficiency. Now, for a naturally aspirated car, and that's what I mean by NA right here. I'm not saying nah, I'm saying NA, naturally aspirated, no turbocharger or no supercharger. Most cars today will be somewhere between 80 to 90% volumetric efficiency. Guess what? With our OBD2 generic scan tool, even with our little scanner interface and our cell phone app, we can actually calculate what our engine's volumetric efficiency is. So to do this, we need the data coming off of our scanner, and we need a volumetric efficiency or VE calculator. And this is super slick. So I'm going to click this link right here. And it's going to open something up, and I'll change my screen share to make sure that we see that. So give me just a second here. And there it is. Okay, so let me get it going. So the link opened up, and here you can see my OTC volumetric efficiency calculator. Okay, so what do I need to know? I need to know the intake air temperature sensor. I need to know the RPM level of the engine. I need to know the mass airflow going in the engine in grams per second and the size of the engine. So let's say I'm just going to put some numbers in here. It's at 90 degrees. I'm at, let's say 5,000 RPM. And I have 200 grams per second of air going in the engine. And let's say I have I'm going to say a 2.0 liter engine. Well, maybe I should go to a 3.0 liter engine. You can still see boy, that's really good volumetric efficiency, isn't it? Let's say I'm a 5 liter engine. There we go. So it comes up with 83% volumetric efficiency. Now, to do this test, what I will say is follow these instructions. So let's highlight these suckers out. The engine must be at operating temperature. During a road test, I have to go to wide open throttle and record the data. Okay, what am I recording? The intake air temperature, the RPM, the mass airflow, the engine size in liters. I probably know what that is off the underhood label or off my specifications. Okay, so really I'm recording these 3 things, and all those things I can get with my OBD2 generic data. So I go for a test drive. I get it where there's, an abandoned piece of highway, and I floor it. I go to wide open throttle and I do my scanner recording so I can get what the intake air temperature is, what's the RPM, and what's the mass airflow. And what I do is I look at the highest readings at wide open throttle. Okay, so I get, highest RPM with the most amount of air going in the engine. Those are the numbers that I put in here. And from that, I can then use this calculator to calculate what my volumetric efficiency is. Well, as it says here, most cars these days are between 75 and 90%. And I said really between about 80 and 90%. And so why is this valuable? Well, because if your engine doesn't come out between 75 and 90%, that's telling you, hey, something's wrong. Now, it could have a restriction. If I had a really restricted air intake or a really clogged up exhaust, like I had a plugged muffler because the catalytic converter started to fall apart, all those things would make this number go down. But you know what's more common than both of those? My mass airflow sensor. Because remember, in that data, one of our critical pieces of information, and let me make sure I change my screen share, there we go, was we took the amount of grams per second of airflow entering the engine, and we typed that into that calculator. So if I don't have a restricted exhaust and rats didn't build a nest in my air intake, the most likely cause would be a contaminated mass airflow sensor. And this is a great way to diagnose this. So I see this happen quite often, and it happens on Fords, it happens on Toyotas, happens on all kinds of cars where they don't set mass airflow sensor codes. They set lean fuel trim codes because they say, you know what? I keep having to add a bunch of fuel to this engine to get it to run right. Well, remember, if I go back to these charts, let me get to my basic chart here. How do I sense the load of the engine? The load is off my map sensor, or most cars these days actually have a mass airflow. So if the mass airflow is not reading right, it's putting me in the wrong cell. So maybe I'm really in this cell, but the computer thinks, he thinks I'm down in this one. And so he's only commanding 8 milliseconds instead of 13. So then the fuel trim's having to go way positive to get to 13 milliseconds of on time. And he's setting codes for fuel trim. He's not setting codes for the mass airflow sensor because, hey, it is still working. It's not like it's opened or shorted. It is still working. It's just skewed. It's just off. And so this happens quite a bit. You'll get lean fuel trim codes. It's really a mass airflow sensor. You're not exactly sure. Mass airflow sensors are usually pretty expensive, so I wouldn't want to just throw one on there. And yes, they can be cleaned if you use the appropriate cleaner. So I'm trying to get back to my picture here of the cleaner. And they also don't like aftermarket air filters that are oiled because the oil can go back and coat that sensor element and throw them off. So yeah, you can clean them. Sometimes they get so contaminated that even cleaning them doesn't work, and you have to replace them. And if you're having to put a $300 or $400 sensor on a car, I don't know about you, but I want to be pretty sure that that's going to, be the right diagnosis. So a way for me to figure that out is to use that volumetric efficiency calculator, knowing that if the engine is mechanically sound, its VE should calculate right. If it doesn't calculate right and it doesn't have a restricted exhaust and everything else with the engine looks pretty good, then the most likely cause is that my volumetric efficiency numbers are going to come out low because the mass airflow sensor is not giving us the right information. So if I change this, and if I said, we were only 150, you can see now I'm at 62 on my volumetric efficiency, which you'd say, hey, whoa, if you're not working on, a car from the 50s, 62% of volumetric efficiency would be way too low. So anyways, hopefully that makes sense. The volumetric efficiency calculator is a great tool for you to use to diagnose defective or contaminated mass airflow sensors, and to verify what's going on with your fuel trim and stuff. And by doing that, it's kind of given us some insight on what's fuel trim and how we can use it to establish condition and all that type of stuff. So hopefully that made some sense to you. Very powerful tool that only requires generic scan tool data. Pretty neat stuff. So let's do some conclusions here for tonight. So again, we always want to leverage as much information as we can from our scan tool. So that could be things like using the volumetric efficiency calculator, right? It could be putting the scan tool in a graphing mode, or using custom data lists and stuff tailored to your code. Of course, you're going to now use your O2 sensors and fuel trim to establish a condition. If is the engine running rich or is it running lean, right? If it's running too rich or too lean, that'll give you all kinds of issues. And so if I have a lean fuel, fuel trim that's positive, and so it's indicating that I'm running lean, it could be something as simple as a restricted fuel filter. It could be vacuum leaks, so anyways, very important thing is to look at that fuel trim, because it gives you some feedback on how is the computer kind of correcting itself. Obviously, you can see now that the volumetric efficiency calculators can be pretty useful, but it's not just about the scan tool. It's really about how you use the scan tool. And that's why I said you are the best diagnostic tool here, right? It's not just about what scan tools you have in your toolbox. It's how well do you know how to use that tool, and what's your knowledge of, fuel injection and engines and what they need, really putting it all together. So hopefully that makes sense and you guys got some stuff out of it. What I want to do real quick now is actually go just a little step further, and we're going to look at one of your classmates' vehicles and some problems that were on it. Now, I didn't get all the data from this student, so we can't go all the way as far as coming to any type of conclusion on the diagnosis, but I want to share with you guys how I would approach it. Okay, so here we go. And we'll do this pretty fast because I know we're running a little long on time. So the student's car is a 2001 Toyota Corolla. This is what a 2001 Toyota Corolla looks like. So I put a picture of a Corolla up there. So that's the car. The car has a check engine light on. It's got a bunch of problems. But what I gathered from what they wrote down, their biggest complaint is, hey, they're cruising down the road and they come to a stop and the car dies. And unless they're constantly giving it throttle with their right foot, it wants to die out. So that would be pretty frustrating to drive, right? So what codes do we have? We have a P505 for idle speed controller. This is before throttle by wire. This car has a throttle cable. We have a P440 for an evap malfunction, P0300, and a 442 for evap. And these codes could be related or they could not be related. My preference of how I would prioritize this is, what's the drivability complaint? It dies when it's coming to a stop. I'm going to attack the codes that I feel are directly related to that a little bit more. Now, if you think back to that 8-step troubleshooting process, right? We had verify the customer complaint. Well, we've done that. The car does die. It does have a check engine light on. And step 2 was pull codes. My step 3, with the pulling codes, of course, we would record that. We would look at freeze frame data, right? And I don't have freeze frame data on this car. But then as we move down, I said, hey, does the data support the codes? So let me clear this up a little bit and give myself some room to draw. So here's the codes. There's the car again. So does the data support the codes? And really, what do I want to do? I want to establish. And so what would I look at? I would look at fuel trim. Because establish a condition, I would be, okay, well, is this car running rich or lean? Right? Rich or lean? Well, if if I look at this and I see fuel trim and it says, hey, you're lean, I'm going to be looking for things like vacuum leaks. Also, a car that's running lean, that could be causing that misfire. So again, a lean running air fuel mixture relates to a misfire. I'm going to look for things like vacuum leaks. I might dig in there, dig in the ignition. Maybe the misfire actually is is throwing off the fuel trim. But if I'm running, and one other thing is that this could relate to the evap system, because we have some evap codes here. Evap is your evaporative fuel emission system. It's basically going to pull any vapors off the gas tank. Well, if it's always purging the gas tank or something's wrong with that, or that's cracked, the lines are cracked or broken, the evap system could be acting possibly as a leak. So that kind of ties those things together. So again, how do I know which direction to go? Well, the data that I would look at would be fuel trim data. And depending upon what I saw with fuel trim, that would tell me, you know, do I go for a lean type of situation? Or maybe I go down the road with a rich type of situation. The other thing I said is you always want to, you know, do some research, right? So if I change my screen share and I go back to the internet and I go to shop key here, you can see that I put in the vehicle, the Toyota Corolla. I put in that P505 because it's for the idle speed controller, and I can go in here to OEM testing. And I just started reading to learn a little bit more about this code and this circuit on this car. Because maybe you're not sure, well, does the data support the code? Well, notice it says that the ECM operates the idle air control to provide warm up and feedback for target idling speed. So there's a target idle. So maybe what's programmed in the computer is it wants to idle at 800 RPM. And if it's not able to maintain 800, if it varies greatly from the target speed, that's what's going to cause it to set this code. So that just told me how this code gets set. There's a target idle speed programmed into the computer. If it's too far away from it, boom, it's going to set that code. Now notice that possible causes could be that there's an actual problem with the idle air control valve, right? Or it's electrical circuit, okay? Or maybe something with the air conditioning, like the AC's on, but the computer doesn't know it's on. Or there's an air induction system malfunction. Now, what would that be? That would be something like a vacuum leak, or maybe the air boot between the mass airflow sensor and the engine is ripped or torn. So I have a leak there where I have false air, or as I like to call it, pirate air getting in behind the mass airflow sensor. This one here always freaks everybody out. They say defective ECM, and they kind of gravitate towards it. Oh, the computer's bad. No, it's saying that, hey, if you had a defective computer, that could possibly set this code. That's usually the least common thing out of this whole list to stop. So what I do in my mind is I just cross this thing out, because there's no way for me to really test a computer directly. So what I got to do is test all the other stuff. And if everything else is okay, then I start looking at that computer. So I just cross them out and I focus on all these other things. Again, if it's too far away from the target idle speed, that's why I would set this code. And the biggest thing here is air induction system malfunction, which could be things like vacuum leaks, stuff like that. So let me switch this back to my PowerPoint. So now you kind of see how I would divide it up. If the fuel trim didn't look too far out of whack, you know, I might go with some just common things. Like if there's no vacuum leaks, the fuel trim looks good, I might then jump into testing that idle speed control motor directly. And I would also look at the throttle body. A throttle body on the front side can look like this right here, which it doesn't look too dirty. On the back side, though, it looks like this, and it's really clogged up. In fact, here's the passage for the idle speed, and you can see how clogged up that is. So a common thing with an idling issue on vehicles is just that the throttle body gets all dirty, it gets all gummy, and then that's restricting the amount of air flowing around it into the engine. And again, if it causes the idle speed to vary too much from what's programmed into the computer, it would start setting those codes. It could start stalling. So, there's no substitute for a good physical inspection of the vehicle, that good thorough visual inspection. You can diagnose a lot of stuff that way, especially if you couple that visual inspection with your scan tool. So you know the codes, you know the complaint, you're looking at things like fuel trim. So if you say, hey, it's running lean, I'm looking for vacuum leaks. Or maybe it's not running lean, but the idle speed's really low and it wants to stall out. I'm going to look for a dirty throttle body. So anyways, that's how I would approach this. Unfortunately, I didn't get more information, more data from the student. I would have liked to see some scan data and with some fuel trim numbers. I would have liked to see the freeze frame information. All that could have kind of gotten us further in this diagnosis. But I at least wanted to share this with you to kind of show you how I would approach this vehicle. And it's a mix of your scan data, right? And your knowledge of using your scanner and pulling that data and what to look at. And then your a good thorough visual inspection. And of course, a lot of your smarts about how things work. And of course, how do you develop those? Well, you take engine performance class, you read your books and you read your service information like I just showed you tonight. So hopefully that makes sense to you guys and you got something out of that. So as I pull this thing, as I pull this back, you change my screen share. I'll go back to Google now and get back to our class here. And that's really what I wanted to cover today. I just really wanted to teach you guys about fuel trim and how important it is to leverage that because it can help you establish a condition. And that's a big thing to do. I want to know, is the engine running rich or is it running lean? If I have any type of engine drivability problem, whether it's a lack of power, it's a stalling issue, it's a surging, it's, is it running rich or is it running lean, can really give me a good direction to go as far as my diagnosis, and fuel trim is a great way to get there. I also gave you that tip, that great tech tip on using the volumetric efficiency calculator to diagnose defective mass airflow sensors. And so we are going to have some upcoming assignments on that. That's going to ask you guys to go out and do a test drive and do volumetric efficiency calculations on your vehicles. And I'm really excited to see some of your data and what you guys find from that. So as we wrap things up, does anybody have any questions about this stuff? You can shout them out. You could put them in the chat. I'd be happy to take care of those. Well, it might be that I've blown you up, too much information. Feel free you can call, you can email me through the week, and we can always throw it in a future class. I hope you guys enjoyed this. I'm glad to hear that some of you did. Really, really powerful diagnostic information. So we won't have class next week, but we will kick off the following week. And I got to kind of see how everything kind of fits into place. I want to try to get it done before Thanksgiving comes around. But I have one more full presentation for you guys where we're going to do more case studies and put into practice more of these things we've been learning about with scan data and diagnostics as we kind of wrap this thing up. And then I'm going to kick it off to you guys because you guys have some snap-on training you could do if you want to kind of go to the next level and kind of round things out. So with that, I'm going to say Good night. Oh, Damien has a question about diagnosing a fuel pressure sensor. Whenever you're doing any type of sensor, right, you want to, compare that sensor versus something else. So if it's a pressure sensor, I'm going to see what does the sensor say its pressure is versus what is the pressure really. So I would put on a real fuel pressure gauge and see what the real fuel pressure was on my mechanical gauge and compare that to what the sensor says. That's the first thing I would do. And then I would kind of go from there. If the sensor's off and the electrical circuit's good, it's most likely a defective sensor. So thank you for being here, and we will catch you on the next session. All right.